we've talked a lot about water on the moon and water prospecting. Obviously, there's a lot more prospecting that we'll have to do in order to know whether or not and how we can start mining the water ice. But it's not too early to start developing the technology to take that water and turn it into propellants. So that's what we'll be talking about today. Now, some of this we've actually demonstrated a while back. Back in 2010, this was under the Constellation program. We had a field demonstration for ISRU Technologies in Mauna Kea, Hawaii, where we took the local material, it's called tephra, similar chemistry to lunar regolith, fed it into a carbothermal reactor, used concentrated solar energy to melt the regolith and extract oxygen in the form of carbon monoxide, which was then reacted with hydrogen to form methane and water vapor, which we then condensed out and electrolyzed, dried the oxygen and split it into hydrogen and oxygen, which we then liquefied and used it to fire a small thruster on a sintered pad that was actually created with the same solar concentrator earlier in that demo. So a lot of really good work done back in that time. It all pretty much stopped right at the end of the Constellation program, but we're able to start picking up where we left off now with the return to the moon. One of the things that we're doing with this project is looking at some of the parts of this demonstration where we were using consumables, specifically getting the water purity to where it can actually be split in electrolyzer. We use consumables in this demo, and then also drying the oxygen to the point where it could be liquefied, also use consumables. So the focus of this project, or at least this task within the resource project, which is a survey project, we have a task to demonstrate the end-to-end production of pure dry oxygen from a contaminated water source. So we started this task around the beginning of fiscal year 2020, and there were a lot of parallel efforts, mostly funded by STMD, that were developing similar technologies that we could leverage with this project. So we've been assessing and monitoring all of these various contracts that are looking at either water capture, water cleanup, water electrolysis, and seeing how we can leverage those activities and to help support those efforts with this project. So the first step is a water purification. If we want to split water into hydrogen and oxygen using a proton exchange membrane, which is what's been used on the space station for the last 20 years, this is what is producing the oxygen on the space station for the crew, comes from the water source. Proton exchange membrane electrolyzers require ultra-pure deionized water because what you're doing to split the oxygen is you're actually inducing an electric current, and deionized water will not conduct an electric current. So that keeps the electricity where you want it in the stack instead of electrifying your whole system. It also prevents damage to the stack. The space station electrolyzers actually have multiple failures due to water purity issues. So this is something that we need to overcome if we were long-term in order to actually turn lunar water into hydrogen and oxygen gas. So some of the efforts that we've been investigating, there's actually two. Paragon Space Development Company has worked on a method for freeze distillation. So they've looked at a mixed volatile stream, taking the volatiles that we know to be mixed in with the PSRs from LCROSS data. And they had a test bed where they actually were able to extract water, just targeting water specifically through freeze distillation, allowing other volatiles to pass through. They sent us their water samples and we analyzed all of those. It looked like they did a pretty good job of purifying the water. It overlaps with distilled water, but there's still some polishing steps that we'd have to get to make it ultra pure. Now on the JSC side in-house, we also were looking at the contamination from particulates because the water is mixed with regolith, and so you need to be able to separate the water vapor from any of those particulates. So we did some experiments where we mixed the water with regolith, vaporized it, condensed it, and use a submicron filter to separate the particulate, but there's still some that gets through and causes some contamination. So we were able to quantify that by analyzing those samples as well. And we were to get, a little bit more pure than tap water, but still not quite as pure as distilled water. But we think we could take that product and use something called electrodeionization, which would not require consumables to get to the point where we could feed that into a water electrolyzer. Now, all of that, the purity is only important if you use a proton exchange membrane. That's only one way to split water. The other way would be to use a solid oxide electrolyzer. Now, solid oxide electrolysis has been demonstrated on Mars to convert CO2 into pure oxygen. So that does have some flight heritage. The same company that developed the MOXIE instrument recently completed a tipping point project to use the solid oxide electrolysis technology to split water. So that doesn't require the same level of purity. And it produces pure dry oxygen. The downside is you have to operate it at 800 C. But all things considered, the SOE method would actually be slightly less massive than going with the proton exchange, and that's because it doesn't require any radiators to reject the waste heat. Solid oxide, since it runs hot, any waste heat can just be used to keep it warm. So what we're proposing over the next year is to combine some of these efforts, take the best of all these different technologies and combine them together to demonstrate this end-to-end process without any consumables. So we'll use some of the technology that Paragon has been investigating initially to separate water from other volatiles, and then take the humid hydrogen stream and feed that into a solid oxide electrolyzer. So we can, so the SOE would produce pure dry oxygen, but we'd still need to dry the hydrogen. So one of the things we've been exploring are ways to dry the hydrogen without consumables. We have a regenerative gas dryer that we've just actually started testing, collecting data a couple weeks ago, and the initial results look pretty good. So we can regenerate this desiccant with vacuum only, so it doesn't require any power, and we can get down to less than 20 parts per million of water. So it's still some work to be done, but it looks like we have a pretty good method for drying hydrogen as well. The most difficult part will be liquefying hydrogen. This is an area that needs more investment. Current state of the art for hydrogen liquefaction is pretty heavy. There are some more advanced techniques on the horizon, like active magnetic regenerative refrigeration, that at least will reduce the power required. I'm not sure what the mass would be of that type of system, but this is one of the challenges with using the lunar water to make at least liquid hydrogen. Is just very energy intensive. It's difficult to pull something out of a substance that's already cold. You need to get down to 20 Kelvin to liquefy hydrogen, but this can be done. But it's not the only way. There's also the approach of using the hydrogen sourced from lunar water to actually make liquid hydrogen or liquid methane, which would be a more Mars forward approach. So if we start off using the carbothermal process that you heard of initially to extract oxygen from a regolith, while we're doing the prospecting campaign for the water, once we get the water online, we can feed that into the existing carbothermal system and use it to produce both oxygen and liquid methane, which is what we would do on Mars. So it got a nice moon to Mars architecture. And it's important that we do this because this will significantly reduce the cost of a sustained human presence on the lunar surface. So if we have some time for questions, I'll go ahead and take questions.
Hello? Yep, there we go. Thank you. So we actually have time for one question. If anybody has a question.
Yeah, there are multiple steps in this. The one that was interesting that you mentioned was the addition of the regolith into the water, and then you did steam generation. So were you using some solar heating of this particle mixture to generate the or release the water and purify it?
Well, so in our experiments, we weren't using solar energy for that part of it. We're just using the traditional resistive heaters. We think that process will most likely take place in a PSR, and we hope that in the future we would have something like RTG waste heat or nuclear reactors in a PSR to actually drive that process. Otherwise, you're having to carry the water up out of a crater.
Okay, so that's what I'm.
In which case, it'll most likely vaporize before it gets to the sunlight, unless it's sealed. Good question.